Okay, this is a neat example, and it's based on real life. Back in the 1940s, as you might imagine, the science on nuclear bombs was pretty classified. There wasn't much public information given, and in particular, information regarding the energy released during a nuclear explosion wasn't available. So that what I mean by that is the number of equivalent kilotons of TNT that an equivalent that nuclear bomb generated when it exploded. By the way, nowadays energy is measured in megatons. Nuclear bombs are much more powerful. So the energy released during the explosion wasn't available publicly. There was a very famous fluid mechanics professor, G.I. Taylor, from the UK, who was asked back in 1941 to predict the dynamics, of a blast caused by a nuclear explosion. And what Taylor did is he actually just did a dimensional analysis. He said that there was a finite amount of energy, E, that's suddenly released in infinitely concentrated form. So basically the nuclear bomb, the way it worked was you compressed some fissile material to a very small volume, and that caused fission to occur in the material, and that's how you got your nuclear explosion. So it's a very small volume that he was dealing with. So he just assumed that it was infinitely concentrated, and that the resulting blast wave had a radius r that would then propagate out into the surrounding atmosphere. You can see that down here in the set of pictures here. This is a nuclear bomb, just still frames from a video showing the blast wave, the edge of it's given right here as a function of time. Right, so he said that blast wave with a radius r propagates into the surrounding atmosphere, which has some density and specific heat ratio. The specific heat ratio, if you've had thermodynamics, is a thermodynamic quantity of the specific heat at constant pressure over the specific heat at constant volume. So that blast radius is propagating into the surrounding atmosphere with the density and specific heat ratio as a function of time. So he said that release of energy was a function of those variables. And then he did a dimensional analysis on that, and he found that there was a very simple relationship between the blast radius and these other variables. And then he used some declassified photographs from the first nuclear explosion at the Trinity test site in New Mexico. Excuse me. So he used his dimensional analysis combined with these images you see here, and was able to estimate the energy release to within a very good accuracy. And that really freaked out the American government, because they thought that somehow someone had leaked information about the energy release, but Taylor didn't receive any information from a spy or anything like that. He was just able to figure it out from a dimensional analysis and some photographs. So a really neat example of dimensional analysis. So we're going to duplicate that analysis here in a much more simplified form. Let me give myself a little extra page of paper here. Okay, there we go. And by the way, if you want to know more about it, you can read the paper here and see how we did the more detailed analysis. We're simplifying things a little bit here. All right, so step one is we said that the blast radius was a function of those variables I described before: time, the energy release, which is sort of what we're trying to find, the density of the surrounding atmosphere, and the specific heat ratio. As far as knowing that the density and the specific heat ratio are the important quantities that affect the blast radius as a function of time, that comes from some more sophisticated analysis. Just knowing something about this has to do with just the propagation of shock wave out into the atmosphere. So it's beyond what you currently know for fluid mechanics. So just take it as a given. This comes from some other analysis here. Okay, so our second step in our dimensional analysis is to describe these variables in terms of basic dimensions. So the radius is a length, time, of course, is a time. The energy release is actually just energy, which would be like force. It's like a work term, so it'd be like a force times a length, or mass length over time squared times a length, or mass length squared over time squared. I like to do everything in terms of mass, length, and time. So that's energy, again, just force over a distance, force times a distance, and then I just simplified it down this way. The density of air, or of the atmosphere, is just mass over length cubed, and specific heat ratio is actually dimensionless. It just, the specific heat ratio for air, for example, is 1.4. It's just a number. All right, then we figure out our number of pi terms from the Buckingham pi theorem. That's just our number of variables minus the number of reference dimensions used to describe those variables. So our number of variables is up here. We have 1, 2, 3, 4, 5. Number of reference dimensions, well, you look down here, we certainly need a length, we certainly need a time, and we definitely need a mass. And then the energy has all those already. So we need 3 reference dimensions, mass, length, and time. So we'll have 2 pi terms. So to find those pi terms, we'll choose some repeating variables. We'll choose 3 of them because we have 3 reference dimensions, and those 3 variables will come from the right-hand side of the equation. So the ones that I'll use will be, actually, we'll all have to use the same ones. Normally, the choice of repeating variables is not unique, but here it is, actually. And I'll explain in a moment. So I'll choose t for the time. I'll choose rho naught for the mass. And I'll choose e for the length. I don't want to choose r as length because that's on the left-hand side of the equation. Okay, that's a dependent variable. I just want to choose from my list of independent variables, which are on the right-hand side. And the reason I said that these are unique in this particular case is because we only have 4 variables here. The specific heat ratio is dimensionless, so we can't use that to make anything dimensionless by. So we don't want to choose that because it doesn't have a mass, length, or a time in it. So that just lives as these 3. So in this case, it's unique. So now we make our terms dimensionless using those repeating variables. So we'll make r, our first pi term, we'll make that one dimensionless. So it'll be r times t to the a, rho naught to the b, and e to the c. We'll express that in terms of our dimensions. So on the left-hand side, it'll be mass, length, time, each raised to the 0 power, because anything raised to the 0 power is equal to 1, so it's dimensionless. Dimensions of r are just length, so L over 1, t, just time raised to the a, density is mass over length cubed raised to the b, and the energy we said was mass length squared over time squared raised to the c. And then we'll go ahead and look at each of those dimensions separately. So we have mass, so on the left-hand side it'll be 0, on the right-hand side it's going to be a b plus a c. So we have the 0 here, m to the b, m to the c. So we're just dealing with the exponents here. Now we have length, 0 on the left-hand side, it'll be 1 minus 3b plus 2c on the right-hand side, and then time, 0 on the left, we'll have a minus 2c on the right-hand side. Okay, so now we have this system of equations that we have to solve. This one's a little more complicated than some of the other examples because you actually have to solve them simultaneously to figure out what they are. I'm not going to go through the steps in that, but it's just it's kind of a linear algebra problem. You just substitute in or do some sort of like Gaussian elimination, what have you. So, but when you work it out, you get a is equal to the minus 2/5, b is equal to minus 1/5, and c should be 1/5. So that our first pi term will end up looking like r times the density raised to the 1/5 divided by t to the 2/5 and e to the 1/5. So that's our first pi term. Our second pi term is already dimensionless. It's the gamma. So that's our other non-repeating variable, but it's already a pi term because it's dimensionless. So pi 2 is just simply the specific heat ratio, gamma. And the next step is just to verify that indeed these are dimensionless quantities. So pi 2 we already know is dimensionless. Pi 1, that'll be like a length times the density to the 1/5. So that'll be L cubed over 3/5 over m to the 1/5. sorry, I have that flipped upside down. Let me fix that. Mass to the 1/5 over L to the 3/5. And then we have divided by time to the 2/5, so that's 1 over T to the 2/5. And then we have the energy to the 1/5, which will be T to the 2/5 divided by M to the 1/5 divided by L to the 2/5. Okay, so what I'm doing is I'm just putting the units associated with each one here, just over here. So here's my length, my R, my density, my time, and my energy. So let's see what we have here. So in the denominator, we have L to the 3/5 here and L to the 2/5, so that'll add up to be L to the 5/5, or just 1. So that cancels out. Here we have T to the 2/5 cancels out with that, T to the 2/5, and the mass to the 1/5 cancels out with that one. So this is okay. This pi term is indeed dimensionless. We're just verifying it. That was step 6. So step 7 is now rewriting our equation in dimensionless form. And that would be now our equation in dimensionless form. Okay, so now we know that the density of the atmosphere and the specific heat ratio are well-known quantities, and they're constants basically for a standard atmosphere. So I can rewrite this equation in a slightly different form. I can write it as R over T to the 2/5 e to the 1/5 is equal to rho naught to the 1/5 times this function of the specific heat ratio. But this is basically a constant, right? It's because the atmospheric density and the specific heat ratio, it's just whatever it's going to be for atmospheric conditions. So then I could write that the radius is just some constant. Let me call it C1. It's just some constant C1 times T to the 2/5 times e to the 1/5. So that's the expected relationship I have for the blast radius. I expect that the radius should go as the time to the 2/5 multiplied by the energy released to the 1/5. Let me rewrite this equation in a slightly different form because we're dealing with all these powers. It'd be nice if I didn't have to do that. And the way we can deal with that is to rewrite it with a logarithm. Okay, so I'm just going to take the log of both sides of this and rewrite it in that manner. Okay, and okay, so let me go ahead and do that. So, and here I'm just going to do the same thing that G.I. Taylor did. He used a log base 10 when he did the logarithm. So log R on this side, then we'll have 2/5 log base 10 of the time. And then I'm going to combine together the C1 and the E terms. So this will end up looking like log base 10 of C1 plus 1/5 log base 10 of E. And then let me go ahead and, I guess I didn't really combine the C and the E, I just rearranged them. And then let me multiply by 5/2 so I can get the, again, I'm just trying to get to the same form that G.I. Taylor had. So he multiplied by 5/2. So that you're left with this kind of expression. So this is just the same equation that I boxed in here. It's the same equation as this one. It's just written in a log format. And the reason for that is because when things are raised to a power, kind of like here, this is to the 2/5 and the 1/5, when you take the natural log of that, it looks like a line with a certain slope. Okay, like if I had, for example, y is equal x to the n, and I took the natural log of both sides here, you'll see that this kind of looks like the equation of a line. If I just made these different variables, let me call that y prime is natural log of y and x prime is natural log of x, then this equation ends up becoming y prime is equal to n times x prime. So you can see that this power law relationship can be shown as kind of like a line relationship, but the y prime and x prime are really natural log. They're right here, natural log things. So that's why we often do this, is that we can convert power law behavior into linear behavior when we take the natural log. So now that we have this expression, for a given explosion, we should then expect that the blast radius should follow a straight line when the radius is plotted in this manner as a function of that. And then the offset, so this is like the equation of a line, with the offset being related to the total energy released. So like this is like the intercept. And so that's what, and then this constant here, this comes from this kind of this relationship here, which is outside the scope of our analysis, but it has to do with the way compressible gases behave, which would be the case when you're dealing with explosions and shock waves and such. All right, so anyway, so this is what J.I. Taylor did, and he ended up with this kind of a picture here. So this is a plot of that 5/2 log base 10 of the radius and the log base 10 of the time. So just remember this picture up here. Here's log base 10 of the radius, log base 10 of the time, and then this is like the intercept. So that's the intercept right here. The X, or the cross marks here, come from this picture, this set of pictures up here where he was just measuring the radius. Let me put that in a different color so you can see it better. Just measuring this radius as a function of time. Right? So he actually took those photographs and made that measurement and ended up with this kind of a plot. And from this intercept here, he was able to figure out the release, the energy release, right up here, from the nuclear bomb explosion. Right? So he combined some dimensional analysis to get this kind of relationship with some other analysis to figure out what this kind of constant is right here. That's outside the scope of what we're going to do in this course, but he combined it with some additional analysis so he could figure out what that quantity was. And then he just plotted the data from the publicly released images, and he could use that intercept here to relate that back to the energy release. And what he found, I've kind of described it right up here, is what he found was he predicted the energy release to be about 23.7 kilotons of TNT for that particular explosion, and the actual release was about 20 kilotons. So he had a very good estimate of the energy release, and it was based on doing a dimensional analysis combined with the publicly available images and with some additional analysis to deal with the compressible flow aspects of the problem. And of course that, like I said, that at the beginning of the example, that really freaked out the American government, figuring that somebody must have released some sensitive information, but in fact, he didn't need that. He could just figure it out from the analysis that we just described here. So it's kind of a neat example of dimensional analysis and the power, so to speak, that it can have in being able to be useful for scientific investigations. Okay, we'll go ahead and end the example there. Hopefully you enjoyed this one.